Okay, apparently when you plug your phone in, it stops the video. So we left off showing that we have a minimum cost when the radius of the can is, or it seems as if we have a minimum cost when the radius of the can is the cube root of 300 over pi, or about 4.57 centimeters. All right, so we have to check that it's a minimum. We know that we can't have a minimum cost when the radius is 0 because we would have no can and it wouldn't satisfy the condition that the volume has to be 1,000 cubic centimeters. So I'm only going to check R is equal to 4.57. I'm going to check how the derivative behaves to the left of 4.57 and how it behaves to the right. Pick any number to the left. I'm just going to simply pick 1. We put 1 into the derivative. We don't need to know the value. We just need to know if it's positive or negative. So if we put 1 into the derivative for r, so this is r, we get 0.2 pi minus 60. Well, 0.2 pi is a very small number. It's a fifth of pi, which is only about 3. So this is a very small number, minus 60. We know this output's going to be negative. You can confirm that by putting it in your calculator. So therefore, the cost decreases until we hit 4.57, approximately 4.57 centimeters for the radius. So I'm going to pick a number a little bit to the right. Let's just say 5 to the right of that critical number. And let's just put it in our calculator for confirmation. I'm going to do 0.2 pi times 5 minus 60 over 25. And we see that we get a positive output. I don't care what the output is, I just care if it's positive or negative. So once we hit this radius, the cost of the can is going to start increasing. So we must be using more top and bottom than we would be using sides after that point. So this is going to be a minimum because the cost decreases, then it hits that point and increases. So we have a minimum when our radius is about 4.57 centimeters. And I'm just using that because that's really difficult to write, but make sure you read the directions carefully. If it wants the exact value, it will specify that, or it will just say find the radius. If it tells you to approximate to however many decimal places, then that's what you're going to do. All right, so now it says find the dimension of the can was the original problem. So what does H equal? Well, we go back to our constraint. Remember that the volume, which was pi r squared h, had to be 1,000 cubic centimeters. So we know r, so now we can find the value of h. So if we wanted to find the exact value, we'd have pi, then we'd have the cube root of 300 over pi squared times h equals 1,000. Right, we're going to solve for h by dividing both sides by this whole mess, and we get h is equal to, whoops, I lost a 0, don't lose a 0, 1,000 all over pi. I'm going to rewrite this as 300 over pi to the 2/3 power. Right? And that's just really horrible to look at. So I did do this on my calculator, and I got a little over 15 centimeters, or about a 15 and a centimeter, quarter of a centimeter high. So the can, so therefore the can, that holds 1,000 cubic centimeters with the minimum cost, will have radius approximately equal to 4.5 centimeters, 4.57 centimeters, and height about equal to 15.24 centimeters. Again, so make sure you know you're going to need to use those other values, R and H, if it doesn't tell you to approximate. All right, one more little tiny problem. This type of problem tends to pop its head often, so we're throwing it in there. Let's maximize the area. All right, but maximizing the area with the specific constraint. We have a rectangle inscribed in a semicircle of radius 2, and we want to find the area, the rectangle that has a maximum area. So again, good time to draw a picture, see what's going on here. I'll show you the setup for this problem. All right, so if we have a rectangle in here, I'm just drawing it here for kicks, right? So here's my rectangle. And rectangle has dimensions, x times y, right? And we want to maximize the area x times y. Well, here we have a function that we want to maximize the area. The area is written in terms of x and y, so we must have some additional information to produce a constraint, because the maximum area of a rectangle would be infinitely large, but we have to fit it into this semicircle of radius 2. So here, we know that this is 2, but notice that gets a little weird here because this side of the rectangle can't go all the way out to the edge, because then it would be not inside of the semicircle. But notice we can use this fact right here from the center of the diameter to that corner has to be 2. So what we have here is that this little rectangle here is going to produce this little triangle. And this triangle is going to do everything we need it to do. So I'm going to pull this triangle out just because I'm going to get a little messy in here. So this triangle is going to help us solve this problem. We know the hypotenuse is 2, and isn't the right side just x? Because that side is the same as that side. But what would be the length of the base or the bottom of the triangle? Well, it's half of this from here to here, which is half of y. So it's 1/2 of y. Right, so this has to be satisfied. So isn't it true that x squared plus 1/2 y squared must equal 4 in order for this rectangle to work inside of a semicircle of radius 2? Right, so that is going to be our constraint. Right, so we're going to pick either x or y and solve for it. I'm going to do x squared plus 1/4 y squared equals 4. I'm going to solve for x. X squared equals 4 minus 1/4 y squared, and x is equal to the square root of 4 minus 1/4 y squared. Now we have to be careful because if we take the square root of something squared, we usually get plus or minus the square root of whatever's inside. But because we know x is the length of the side of the rectangle, we know that we are looking for the positive square root. So now the area is equal to x times y, which is equal to the square root of 4 minus 1/4 y squared, all times y. So that's the function we're going to maximize. I'm going to turn this into 4 minus 1/4 y squared to the 1/2 power times y, because when I'm doing derivatives, I like to turn radicals into powers. So this one is algebraically very tricky. Right, we want to maximize the area, so we need to find the critical numbers of this function. We find the critical numbers by taking the derivative and seeing where the derivative is either 0 or undefined. So let's say the derivative of the area is the derivative of the first, because we have a product. 1/2, leave what's inside alone. Drop the power by 1, times the derivative of what's inside. So the derivative of what's inside is negative 1/2 y. Because the derivative of 4 is 0, we'll bring the 2 out front, drop the power by 1. So this is just, we're using the product rule here. So this is the first, this is the second. So this is just the derivative of the first times the plain old second plus the plain old first times the derivative of the second. Right, so now I'm going to clean this up a little bit. I have my area. The derivative of my area is, well, this is going to be y squared on top, right here. That's going to become the square root in the bottom, and then that negative 1/2, and that 1/2 becomes negative 4 here. It's going to be, I'll leave it like this, 4 minus 1/4 y squared, right, to the 1/2 power. So that's that term. And then it's going to be 4 plus 1/4 y squared to the 1/2 power. So that's the derivative. We need to know where the derivative equals 0 and where the derivative is undefined. So I'm going to look right here. When is this derivative undefined? Well, it's undefined when 4 minus 1/4 y squared is equal to 0, because we'd have 0 to the 1/2 power, which would be 0, and that denominator would be 0. We solve this for y, and we get y equals 4. So if y equals 4, the derivative is undefined. Right? So that's one critical number. Now we need to know, so when is a prime equal to 0? All right, well, algebraically, this is very scary. Negative 4 minus 1/4 y squared to the 1/2 plus 4 plus 1/4 y squared to the 1/2 equals 0. And we need to solve this. So you just got to get a little clever with your algebra here. I'm going to bring this piece over to the right side. So do you agree this is equivalent to 4 plus 1/4 y squared to the 1/2? And that would become positive y squared all over 4 times 4 minus 1/2 y squared to the 1/2 over here. I'm going to eliminate the fractions by multiplying both sides by this denominator. I'm going to multiply both sides by 4 times 4 minus 1/2 y squared. Watch how really nice things happen here. So I'm going to bring this guy over to that side. So I'm multiplying both sides by the denominator, 4 minus 1/2 y squared to the 1/2, and 4 times 4 minus 1/2 y squared to the 1/2, because I don't like working with fractions. But this is the same thing to the 1/2 power. So something to the 1/2 power times something to the 1/2 power is just that something to the 1 power. 4 equals this, and that just equals y squared. Look how nice that turned out. Okay, so now I'm just going to distribute. I get, oops, don't change the number. It's 1/4 right there, right? So now it's going to be 16 minus y squared equals y squared, or 16 equals 2y squared. Y squared equals 8. Y is equal to the positive negative square root of 8, but we're not going to talk negative because the length of a rectangle, the side of a rectangle, cannot be negative, so this is going to be 2 square root of 2. Woohoo! Right, but now we have to check that in fact this is going to produce a maximum, right? Oh my goodness, this is terrible. Let me see, I want to go back to, all right, so the derivative of the area. Yikes. All right, let's see. We're going to do this. We're going to do, I'm trying to think of which derivative I want to use. Let's do y squared over negative 4 minus 1/4 y squared to the 1/2 plus 4 plus 1/4 y squared to the 1/2, right? We are going to do 2 square root of 2. Right, we know it's not going to be 4, so we're going to check the derivative. Yes. So let's really simply, how about we just do 0? That doesn't make things all that terrible. So if y is 0, we get 4 to the 1/2, right? Y is, oh, that whole thing just disappears. And if we put 0 here, we get 4 to the 1/2, which is 2. So that's positive. That wasn't all that terrible. So this is giving us an inclination that this is definitely going to work, right? We can't put 4 in, but if we put a number a little bit to the right of 4, like 3, and pop this into our calculator, we get, let me see, that's going to be 9. This is going to be 3, 9, 9/4. That's going to be negative something. We probably would have to pop that in our calculator. I'm going to leave that up to you, and I'm pretty confident that's going to be negative. So the area is decreasing. All right, so we have a max at when y is equal to 2 square root of 2. So the question says, what are the dimensions of the rectangle? Well, we have to go back to our constraint. Right? Our constraint was let me remind us what our constraint was. X squared plus 1/2 y squared would equal 4. Right? So we know that y is equal to 2 square root of 2. So we have x squared equals 1/2. Well, 2 square root of 2 squared is 8, plus 8 equals 4, right? Whoops, that doesn't work. What did I do wrong? X over, what is 2 squared root of 2 squared? Oh, because that can't be, because that's telling me x is 0. So I lost something here. Oh, I know. That's why. That makes a big difference. All right, so don't do that. Right? The constraint is x squared plus 1/2 y, that whole quantity squared, which is much, much, much different. So we have x squared plus, so notice I saw here that x would have to be 0, but then that doesn't make sense. So we have 1/2 of 2 square root of 2, and we're going to square that much better. So x squared, well, 1/2 times 2 is just going to be 1 square root of 2 squared equals 4. So x squared plus 2 equals 4, x squared equals 2, and x equals the square root of 2. So therefore, our rectangle is 2 square root of 2 by square root of 2 units. And does it tell us? That's it. All right, you survived, we survived. Yoo-hoo! See you guys later.